see. Put my okay, I'm gonna share my screen. What is okay. So this little section of the class is actually fairly easy, straightforward compared to reaction mechanisms and what comes after. So the title of this chapter, it's the same title as chapter 6 in the book. It's the analysis of and correlation of kinetic data. So we'll do what we can to follow. We'll follow the book as closely as possible in this chapter. Sure. Okay. So we'll spend about a lecture and a half on this topic, and this will constitute what the rest of what's been covered for exam 2. And the next lecture, we'll start talking about multiple reactions in ideal reactors after we finish up non-linear regression and comparison of different rate expressions using data. Okay. Now, this section of the class, as we talked about before, is first, can you derive a rate equation given a set of elementary reactions? Can you even can you also understand how some of these elementary reaction sequences give rise to the rate expressions that you see, depending on the collisions and the adsorptions and the mechanism of absorption? And I think your homework treats 5A treats this decently. I will post 5B after class today because it will deal mostly with data analysis and plotting data. So we have quite a few things to go through today, but it's for some of you it will be it should be, or it could be, rather straightforward, and that's what I'm betting on. So the question is, if we derive or postulate, so one of those things, a rate expression, how do we check it against data? And the other similar question is, what kind of experiment do we set up to even get the data? So one of the homework questions treats this idea that you can have two hypotheses lead to the same form of rate expression. So you need some experimental setup to help you figure out which one is correct. And I think question 2C is a difficult question, but I hope that some of you sit and think through it. Sort of gives you a hint of what sort of experiments you can do to test which form of the rate expression would be more appropriate, so you would know which experiment to set up. So both go hand in hand. So the chapter goals the goals for this chapter here, they are the same learning objectives essentially as in chapter 6. What we'll do first, we'll present reactors, and this is almost review, used to generate rate data. So this will be review for most of you. And the second thing we'll do is present the 3 ways the rate law can be determined from experimental data. Also, it can be verified from experimental data. And the first way is the differential method, and I will explain what that is. The integral method, both of these are linearized. So these are linear regressions. I meant to put linear regression. And you also have nonlinear regression, which applies for both methods, both differential and integral. And for this reason, we will learn how to linearize rate expressions. So to be able to plot them. So one way you could plot them is to linearize them, so you can do linear regression. One other things we'll do is a qualitative. This is not in the book, but it's important. Hypothesize the form of the rate expression. So it's so you're looking at the data. Can you sort of guess what the rate expression looks like? And of course, we will do that today, and also the next time is to do some best fit analysis of understanding how to best fit and look at residuals, and fit those and find out which of the rate expression that we guessed sometimes is best, because in many ways, whether or not we derive the rate expression from sequence of elementary reactions, or we guess what it is and we check it, in the data is needed to verify this. So the idea is to obtain best fit values and test for systematic errors. This one we'll actually do on Thursday. We won't do that today. This is for Thursday. Okay, so these are the things that we'll be doing before we move on. So this is what the goal of this chapter in the book are. The first question that we ask, this first probably 45 minutes today, is very qualitative. So the question is, how is useful data generated? So that's the first question. And as you might have guessed, we use our ideal reactors to generate that data. So we use the batch reactors, CSTRs, PFRs. We use them in certain conditions that generates very reliable rate data. And we will talk about those conditions in the next couple of sections. For example, one condition for an ideal reactor for For example, you can say for one thing that we have assumed worked out so far is that all the reactions are isothermal, but that's not the case. Like very almost, I don't know what percentage, but most reactions are not isothermal. So the first thing that there's a couple of things. The first thing, for a heterogeneous catalyst, reactions are run at conditions that controlled by intrinsic kinetics. So that's one way that otherwise the data is not useful. So basically neglecting transport effects. So you can do that. And one way to do that is to use a very thin layer of catalyst so that the transport effects are negligible. Very little catalyst, very thin layer of catalyst. And for most reactions, it is to operate isothermally or at low conversion. So if you operate at low conversion, then heat generation can be minimized, or heat generation as in endothermic, exothermic, can be minimized. So these are some of the ways you would go about. These are some of the ways you would go about generating useful data. Okay. So we talked about how we can do this with our ideal reactors. So one of the first, reactors we've dealt with are CSTRs. They're often called gradient-less reactors. Gradient-less meaning that there's very small concentration gradients, little to no concentration gradient. So that is by definition.
What's the line above say? Operate isothermally or at what?
Let's see, or at low conversion.
Okay.
Yeah. So a CSTR can be thought as gradient-less because it's well stirred, so there's little to no concentration gradient or temperature gradient. So that's it's for that reason it can be an attractive reactor to generate data, and we'll show you what we do. So what kind of data are we looking for to fit our equation? We need rate as a function of concentration. That's essentially what we want to fit it, like in many cases. Sometimes time or space-time as a function of concentration is useful when we develop the integral method, but for a differential method, and we'll talk about what those two mean, but we need rate versus concentration data. So if you look at just the design equation for CSTR, you can write it as this. Okay, so you can write it as this. So what this means that if you measure XA, remember that XA is at the exit of the reactor. If you measure XA and you set FA naught and W, so these are things you know, then you can calculate minus RAs. So you can calculate minus RA. So you can do that for multiple different FA naughts. So for example, you could take a reactor where you change V naught or FA naught. It's easier to do that than to change the catalyst weight or the volume of your reactor. So by changing those, you get different XAs, and you measure XA. Sometimes, however, if you have multiple reactions, if you have multiple reactants, so let's say you have the reaction A plus B equals to C plus D, sometimes it's better to measure all flow rates out, molar flow rates out. Let's see. Because there could be additional reactions, and that goes back to chapter 1 when we looked at, and we'll go back to that again next chapter 7, so that you can account for additional reactions that could occur or degradation. The one key here, now we're only presenting CSTRs, and then we'll talk about in a second why they're not very good for doing the experiments that we want to do, which is ironic. So the key here is to make sure that FA naught is varied, or V naught, one of those two, right, is varied over a wide range. So if you do so, then you get quite a bit of data, just as well as temperatures, a wide range, and then you can also have various temperatures. You can also use something's going on with my so see, you can also vary temperatures. So if you do that, I need to. If you do so, you can generate. You can generate a set of data like this. So you'd have, and that's also a table in the book. This is a typical data you would love to see. So you set up your experiments. You have a certain temperature. Now, you're calculating rate based on your XAs, and then you have multiple species, right? So you have multiple species. So you have your reactions. Yeah. So you can set one temperature and a different temperature, for example. So for each of these systems, so between experiment 1, 2, and 3, let's say you varied V naught or you varied FA naught, you varied some of these, and you're getting an exit concentration of your products and your reactants. Okay, so for each of them, you're gonna get a minus RA. So it's okay if you don't copy this, it's in the book. And you'll get a CA for each, etc. A CB. To, etc. So you'll get this data. And then you would, like I said, to set these up, you would vary either V naught to change CA naught, or you would vary FA naught while keeping V naught constant. So you would get different, and then you'd measure the outlet flows. The problem with this, it is actually difficult to measure. It's difficult to control XA. So this is the one thing to keep in mind. That's why we, in fact, people don't really use CSTRs to do that. It is difficult to control XA. It's just gonna be what it is, and you have to measure it. And if your measurement is not accurate, or it has variations, let's say your variation is 10, 15%. So if your variation in measurement is 10 to 15%, then that means you have to have maybe FA naught or CA naught vary over a 100, over a twofold order of magnitude, so that you can make a difference between first order or 1.5 order, because there's a 10% gap, there's 10% error in your measurement, and that gets amplified when let's say if your reaction is second order. So if your reaction is KCA squared and you have a 10% error in your measurement, so that gets amplified. You have a very large error when you try to plot it. So that's why we find that using reactors where you can control the outlet concentration or the conversion works out best, and we'll talk about that just a minute. Another consideration to make, and this is true for every reactor system, is if you have more than one. Another consideration, let's say if you have K, Ca, alpha, Cp, beta. So now, if you have a system like this, if you feed is equimolar A and B at every time you do your experiment, then you can write this, right? You can write there's a K missing here. So you can write this, and you can determine gamma. But to determine alpha and beta, you have to set up experiments where, for example, you keep alpha constant, but you keep A constant and you change B, or you keep B constant and you change A. So you have to set up experiment like this to determine the individual orders. But if you feed equimolar A and B, you can get the overall order of the reaction. So that's something that you should also keep in mind. So this first part of the lecture today is quite qualitative. There's not much algebra involved. It's just very looking at what we are actually gonna be doing. Another more important type of reactors are differential plug flows. What we mean by differential is that we're not integrating the design equation. That's what it means algebraically, meaning that we're not actually solving for the design equation. We're just using the rate expression, and we're looking at solving for the rate expression by plotting rate versus concentration. If we had an integral plug flow reactor, would be plotting space-time versus concentration, or volume versus concentration. So that's what we mean, the difference between differential and integral. So if we have a differential plug flow, and I will kind of draw out, and that's not in your book, but that's what actually, if you design a differential plug flow reactor, that's what it looks like. So your catalyst is actually right there in the middle. So this is your catalyst. And on either side, you have an inert material or whatever. You have an inert material to filling. You have an inert filling. And you have a very small little bit of catalyst somewhere, smack in the middle or somewhere in your reactor. And then you have FA naught going in, and you have this little length or I guess you can call it delta W. Right, this is like a little bit of catalyst. It's a very small bit of catalyst, and you have, you can say how much is going in FA naught and how much exiting FAE. So if you look at it more of a cartoon, it sort of looks like this. So you have a little bit of filling of catalyst in the middle. It's not taking up the whole reactor. It's only a little bit of the reactor. So that's how you can minimize the transport effects. So you have a very thin. This is, for example, oops. This would be, let's say, A goes to products, and it would be, you'd have these. Okay, so that's what a differential plug flow reactor would look like. And you can, you can do the the mole balance on this as you did before. It's going to look very similar. So you have in minus out plus generation equals 0 because it's under steady state. So you have FA naught minus FAE plus R prime A delta W equals 0. So delta W is essentially your little bit of catalyst that you've put in. Okay, so then you can solve for RA prime. So we use RA prime because you're dealing with a rate that is going to be per mass of catalyst. That's just a convention. So you'd have this system here. Now you can notice that we don't say V equals V naught here because differential plug flow reactors are quite useful for studying gas phase reaction on solid catalyst. So if you're gonna, because if you're gonna study that reaction, you probably can't do it in a batch reactor because it's hard to have a thin catalyst in a batch reactor. How do you determine volume per catalyst weight? So you have to do a few calculations. But here, you are actually putting a very thin little bit of catalyst in the direction of the flow, or opposite or perpendicular to the direction of the flow. So you have, so you can do normal calculations as you would for a PFR. So you can basically say that now if V is equal to V naught, actually not really, you could actually say that so you can calculate the rate as a function of flow of the product out. So you can say the flow of the product out divided by the catalyst weight would be equal to the rate. Now, what you would do, for example, you would change your, well, we'll get to that in a moment, what you should do. And then if you have a constant volume or constant density, as in either liquid or the expansion factor is 0, V is equal to V naught. So RA prime can be equal to V naught concentration of product over delta W. So this would be equivalent ways of writing your differential PFR mole balance. Oh, there's a minus in front here in every single one of them because these are positive numbers. Forgot about those. Okay, so now what approach do we take? The approach is very interesting. So what you do is, if you use very little catalyst, you have very little conversion. Or large V naught. So if you have a large volumetric flow rate or very little catalyst, that CA naught minus CAE can be made very small. Okay, that CA0 versus CA can be meaning that there is very little conversion. So whatever converted is, a couple of percent. Then one thing you can modify. So we're gonna what we aim to show is that what we want to show is the following. We want to show that the minus RA prime here is actually minus RA prime evaluated at CA0. That's what we want to show. And I'll show you and I'll tell you why that's possible. Of course, because you have a concentration in the catalyst bed. So you have concentration going in, you have some concentration in the catalyst bed and concentration going out. So first thing you can say, so we want to show that's the case. So concentration of A in the catalyst bed is CAB, and CAB actually can be equal CA0 plus CAE divided by 2. That's an approximation. That's an approximation that can be made. However, since very little conversion happens, oh no. CAB is almost the same as CA0, since very little reaction takes place. So that means if you replace CA0 here, so you find that so minus RA prime is minus RA prime as a function of CAB. So if you replace that up there, you find that minus RA prime is a function of CA0. So what does that actually mean? What this means is that if you have a system where very little reaction occurs, the rate that you calculate is the initial rate. So this is the very initial rate. So this method can be called the initial rate method. And we'll come back to that in a moment. If you remember, when we were dealing with PFRs, we would say something like CA0 comes in and it hits the catalyst right at the beginning, and that's the highest rate. That's what that is. So that's the rate, the highest. So this initial rate method, so if you vary CA0 from, say, some number, from something close to 0 to some, or let's say if we vary CA from some close to 0 to CA0, then you'll basically get rate for each CA. For each CA, you'll get a rate. Okay. So let's say that this is your, so for each of them, you'll get a different initial rates. So these rates, and this is delta W. So this is very, very, very early. You'll get a rate here for each one. And this is what you get. This is how you get the rate as a function of concentration. Okay. Now so these are all qualitative. So these are basically, when you look at these, when we look at examples in a moment, you'll be able to see how we use this. And it's actually quite straightforward when you see it. But one third example is the integral PFR. The integral PFR is not as useful. So it operates at significant conversion compared to the differential PFR that operates as very little conversion. So essentially you can plot XA and you plot V over FA naught. The reason you can do this is because, let me do a better job plotting this. Okay. So the reason you can do this is that you can, if you look at the design equation, this is the design equation for a PFR. This is just a normal PFR. This is the design equation for it. So if you take the derivative of both sides, so D you can solve for minus RA, which is just dXA over. So what this is just the slope of the curve at every point. So at every V over F naught, or at every XA, you get a slope. So you can, and the slope is RA. So you could have guessed that, I think. So you can get a slope at each point if you can do this calculation. Yeah, so that's how you get the rate data from an integral PFR. It's less useful, and we would actually, I don't think we'll use it in our in this class, but it's, you can calculate the slope at every point for this. So now we're gonna move to the more useful reactor people use is a batch reactor, actually. That's what the most useful one is, except if you have heterogeneous reactions, then you use a differential plug flow reactor, where you can calculate if you have gas phase reactions. It's better to calculate it in a differential plug flow than in a batch. But the reactor that's most useful for us, that we'll use a lot more, is an ideal batch reactor. And an ideal batch reactor, you'd have conversion varying with time. So let's say over time conversion is gonna go up like this, right? This is like a power law based conversion. It could be different, but this is just a power law base. And this is at temperature of T1, right? This is a constant temperature. If you do a different temperature, you get a different profile. So you could also get a system where this is right. This is concentration as a function of time, and you can get the slopes or RAs, right? The slopes of each point. For instance, CA1, you'd have RA, slope RA of the curve. So yeah, so the reason we can do that is because the design equation for constant density is equal to this, right? So this is a constant density design equation for ideal batch reactor.
What is that point you marked on the y-axis? CA1. Oh. Okay.
Yeah. So that would be CA1. You could get CA2 would be a different rate, right? Each of them would have a rate, and then that's how you would get rate versus concentration plots or data. That's how you would do it as a function of time. So at each time, if you set up a reaction with one CA naught, each time you would get a different concentration of A. So you'd measure concentration of A over time, and then you'll get your time versus CA data. And you can take this, if you take the slope at each point, you'll get RA data. So this is just illustrative, and there is a last method. We talked earlier about the initial rate method that is very useful for batch reactors, the initial rate method. And this is the rate that most people use to do enzymatic enzyme reactions. So it's cheap. You can do it in 96 wall plates. So it's very similar to the differential PFR. So let's say you vary CA naught, from over a certain range, and then you react for less than 10% conversion, which you can calculate with standards. Then you would get a plot like this, where this is time. So it's very short times. Short. These are short times. And over the short times, if you keep varying CA naught, you would get rates that are different. So the higher the CA naught, the higher the rate. So you would get these, we could call that, RA4, RA3, RA2, RA1. This would be at a certain temperature. Then we can vary temperature and do this again, right? So this is how this works. And the y-axis is XA, or product formation, right? So if we then look at this, this is essentially the slope. The rate is going to be the slope. Okay, so this is quite qualitative. So this is quite cheap. So if you have a microplate, say if you're doing enzyme kinetics, you can put the enzyme in a plate and you add a different concentration of substrate, and you get an initial rate for each substrate. So then you would plot. So you would have, each of these would be a rate. So it would be concentration per time, right? So this is dCAdt. Right? This would be a dCAdt or minus dCAdt if you're doing conversion. Okay, and then each one gives you a rate of minus RA, which is also a positive number. So you'd have that. You can plot this for each concentration. So what you'd plot is, let's say you have CA, and then you have minus RA. You would plot this. So for each CA, you'll have a different rate until the rate reaches maximum. And then you would end up with a curve that looks like this. For enzymes, this is actually often called the Michaelis-Menten plot. But it's not the only plot that you can have for enzymes. Actually, you can also have a plot that that looks like this. Let's see. My computer acts out. You can have a plot that looks like this. This is called the cooperative Hill function. So this is what's the sigmoidal curve. So you can have different forms. So if you get these sorts of, this is what the initial rate method is very useful for enzyme reactions. And it's that's what we use, that's what I use, that's what most people use. Okay. So now we are sort of done with the qualitative aspects of this. Now what we've done here is we've looked at what reactors and what methods can we use to generate rate data. Now, the question you can ask is, how do you obtain it, the rate data? See, in this little bit here in the initial rates method, I sort of give you a vignette of how you would do it. So if you did initial rates for a batch reactor, you'd have product formation or rate of substrate depletion over time. So you'd get a rate at each concentration of A. And if you're doing it for a short time, that rate would be initial. It would be you would not be reacting for a long time. So it's very less than 10% conversion. So that's how you would get RA data. But there are other ways to do so, to get RA data. So you can see when you first do your experiment, what you're getting here is CA versus time. That's what this experiment is giving you. It's not giving you this. So you have to convert. You have to convert to RA versus CA data. So you cannot directly calculate RA using a differential expression like this. You can't really calculate the rate directly. You cannot calculate it directly from here either, because what you're measuring for integral PFR is XA for every V over FA naught. That's what you're measuring. So if you go up again, if you go to the differential PFR, this one you're also measuring concentration of, so this one you actually could measure RA directly. I think you could measure RA directly because you know CA naught, and well, of course, you're measuring the exit CA. So you still would need to, you'll still need to convert. Okay. Now, so it's very simple, actually. It's not too bad. So in fact, most of the problems will give you RA data instead of giving you time versus concentration or space-time versus concentration data. So yeah, most of them will do that because it's actually quite simple. So the next step is generating, I'll say RI data instead of minus RA, make it generic. RI data, because usually you measure, as I said before, time versus CI or tau versus CI. So that's what you usually measure. So there are 3 ways to convert to rate data. To rate data, either we sometimes call it that or this, okay, from concentrations versus time or concentration versus tau. You of course have a graphical method, and many of you may, if you took numerical analysis, maybe you've seen this. So you have a graphical differentiation of the data. You can have numerical formulas, or you can have a polynomial fitting. In Excel, for example, you can have a polynomial fit. The polynomial fit, I think, is covered in section 614. It's covered there, but we'll also look at it. So one thing we will write here that is not covered is the differential numerical formula. So there is a numerical formula that Wilkes developed in 1969. That is still useful today. And what it is say you're given lots of time versus CA. So if you're given time versus CA data, or you measured time versus CA data, so you can calculate the rates. So the initial point, let's say dCA dt at time 0, is equal to this. You can actually, I think this exists if you Google it. Now delta t is t, in this case, it's t1 minus t0, right? So delta t is tn plus 1 minus tn. Okay, so it's the one before, the one further versus compared to the one before. So you can have any interior points. So these are points in between. So this then minus RA for TI is 1 over 2 delta T times CA I plus 1 minus CA I minus 1. So if you're looking at point number 4, it would be 1 over 2 T5 minus T4 times C6 minus C3, or C5 minus C3. So that's how you calculate any interior point. And then your last point, this is a method that is, let's see, Tn is 1 over delta, 2 delta T of CA n minus 2 minus 4 CA n minus 1 plus 3 CAN. So this is one formula that you can use to calculate your rates from the initial points. So for each point, you'll have a different rate. So that's how you would do it. So there's an alternative, which is a simpler alternative, less accurate. It's covered in the book. The alternative is to get an average rate, which is CA at time 1 minus CA at time 2. So it would be time n time. Let's make it more general. So CA at times n plus 1 divided by Tn plus 1 minus Tn. So that's, you can calculate an average rate there. So if you have lots of concentration, so if you have time and then concentration, you have 0 minute, 2 minutes, 4 minutes, 6, 8, 10. And here you have some numbers, say at 0, it's 10. This would be 10, let's say micromolar or millimolar. And here would be, 8.5, 7.8, 6.9, 5, 4.2. So you can basically calculate an average rate, for example, between these 2 points. You could do that. And then you can also calculate the average concentration that would go with that average rate. That average concentration is just CATN plus CATN plus 1 over 2. So that's another method to make that graph, to convert time versus concentration to an average concentration and an average rate. So to give you, and I made a, I actually turned some of the book examples into an Excel spreadsheet that I built just to show you what it actually looks like. Let's share that screen. Okay, where are we? Okay, so this is in the book. Can you see that that's Excel sheet screen? I can't tell. Maybe you can. I think you can.
Yes, we can see it.
Oh, okay. Let me try again. Okay, so for example, this is a normal reaction where you have time versus concentration. And this is actually, I just copied it directly from the book because it was simple enough to do. You can calculate an average concentration by taking the point before plus the point at time 2 minutes versus plus the point before, concentration before divided by 2, so that's your average concentration. And you calculate your average rate, which is CA minus CA, let's say C5 minus C4 over B4 minus B5. So as long as that number becomes positive, you can, I guess you can put it in any order. It just has to be a positive number. I think I put C5 minus C4. The book has C4 minus C5 over B4 minus B5. But anyway, so it's going to be a positive number. So you can have those two, and you can basically calculate them for every point. And this is the known rate from the book. They tell you in the book that this is a second order reaction. A goes to 2B. They tell you it's actually second order. It's KCA squared. But this is KCA squared. So, and they gave you a value for K. It's 0.24 times K times CA squared. So this is the, oops. Okay, they tell you this. Now, if you plot, and I think in orange is in blue is the plot of average CA versus average rate. So you see that plot here. In line blue is the real rate. So the x-axis is CA and the y-axis is rate. So this is the actual rate. And another way you can do this is using a polynomial. So you could take every point of CA here and basically do a 6th order polynomial versus time. So you could basically take those points and plot them and then generate a 6th order polynomial and then take the derivative of the polynomial, and that would calculate dCA dt at every point. And then you could also plot, right? You would also plot rate and then CA. So you would also plot these. I hope I have it rate versus CA and not other way around. Yes, that's fine. Okay. Yeah, that's all. Like you can see that that's actually the same thing in page 161 in the book. Okay. So if you by doing so, you can basically show that you can generate RA data. You can generate RA data from time versus CA data. And that RA data, once you generate it, you can now, when we do in the next, in just a little bit, you can use it to calculate the reaction order. Here it says the reaction is second order. We could do it the same way, and you can see how we'll do it in a moment. This plot here is showing this is the 6th order polynomial, I believe. Yeah, this is the 6th order polynomial that fits. This is the concentration. So 6th order polynomial, and I take the derivative of it. And then I calculated these dCA dt. This is the derivative of the 6th order polynomial. I just used the Wolfram alpha to get it. Okay. So this is these are the couple of ways you can calculate rate from being given time or space-time versus concentration data. Now, if we summarize really quick, what we've noted, what we see is that there are 3 ways. So we just looked at the polynomial fit. We also looked at on Excel. We looked at this this form right there. Okay, we looked at this. Well, we didn't actually do this one. I don't have an example of it, or I didn't think it was important to do at the moment. But yeah, you can imagine doing the same where you can get a rate in the same way. So. Okay. So now that you can derive minus RA data by given time versus concentration. So the next thing is, can we start evaluating, analyzing, or fit rate data to a rate expression that we either guess or derive from mechanism. So the next step here is to evaluate, fit, or analyze. So depending on what you're asked to do, rate data that you've derived in the earlier section. And the first thing we're going to look at, and this is where it's going to be, this is where we do a little bit of math. That's where it gets a little bit of fun. So it's getting fun. We're going to look at the differential method of linearizing your rate expression. Okay, so we're going to look at this rate expression linearization. And for some of you, it's a review. For others, it is not, but you can linearize the rate expression. So let's look at an example where you have minus RA. This is rate expression linearization using differential method. Once again, the easiest way to understand it is that the differential method, you're looking at, you're using the rate directly versus CA. Okay. Integral method which we'll talk about hopefully before we end, is we actually you work directly with the space-time versus CA data or with the time versus CA data. But here in differential method, we work with minus RA versus CA data. And we just went through in the first half hour or so, or more than that, we just went through how do we get that RA data. Okay. They each have their pros and cons, and sometimes you can't use integral method because your rate expression cannot be integrated easily. So you have pros and cons when it comes to these sorts of things, and then we'll see rate expressions that are very difficult to integrate. As you've already seen a couple, but we'll point them out again. These are the Hinshelwood kinetics can be difficult to integrate. So let's say that you have a power law where minus RA is KCA to the n. So this is A goes to products. A simple reaction A goes to product, and the minus RA is K. So if you take the natural log of both sides, you can get natural log of minus RA equals natural log of K plus n natural log of CA. So you can take the log and expand it. So you can plot this. So if you have RA CA data, you can plot this. Very, very straightforward. You can plot natural log of minus RA versus natural log of CA. And then you'll get a line. If your data fit, you'll get a line. If your data follows a power law, if it does, you'll get a line, a straight line. And the slope of that line is n. Can't erase things. Slope is n, which is the order of that reactant, right? And the intercept is log of k, natural log of k, where you can calculate k. So it's very straightforward to linearize a power law. Now, another example can be the Langmuir-Hinshelwood. So we'll put some indications next to them so you can kind of follow. So let's say now you have your Langmuir-Hinshelwood. Where the minus RA, in this case, it's let's say still a gas phase reaction. A goes to products, and the products don't absorb, right? So only the substrate absorbs. So you end up with something like KCA 1 plus KACA. So one point is like, let's say you have RA data, and you have CA and RA data. Now you want to know how do you linearize this so you can plot something that would allow you to calculate, because your unknowns, these are your unknowns. So you have to plot it in a way you can calculate the unknowns. And what you do is you can invert and multiply both sides by CA. So if you invert, you get minus 1 over RA equals 1 plus KACA over KCA. If you multiply, sorry. both sides by CA. Then you have minus CA over RA is equal to 1 over K plus KA over K CA. So if you plot, CA over minus RA versus CA, this is all the data you actually have. Then if it fits the data, your slope is gonna be Ka over K and your intercept is gonna be 1 over K. So you can calculate your constants in that way. Any questions? Does that make sense? Okay, let me know if you have any questions here. Because your homework 5B will basically gonna be dealing with these sorts of fittings, and your exam will have will likely, I cannot promise yet, have a take-home portion that asks you to do the fitting and then come to class and actually use it for different things. Because you cannot, it's hard for you to get tested on these if you have to use Excel to plot things. So what I'm gonna do, since there are, I think, 14 of you, I'm gonna ask you, how do you, and this is gonna be important, and so that's why I'm happy you're here. So this is an exercise in the book, but it's gonna be important for you to know. So what about if minus RA is KCA over like this? And this reaction is, again, A goes to products. And what the likelihood of this happening is if not it's a dual site mechanism where you have AS star goes to that to give you P plus P plus 2S star. Because here you don't have the product in the denominator, so that the product does not absorb on the surface. So the product goes in the gas phase, but the substrate absorbs on the surface, and then you liberate two sites after the product is formed. So if in this particular case, the denominator is going to be squared. Now you can. This is in your notes from last time, and these are things that will come up in your quiz as well next week. Just to kind of keep in mind. So now what I'm going to do, I think I'm going to try a little 5-minute breakout again to ask you how you would do it. And you can come back in a few minutes to tell me what you found and what you have done. Let me see if I can make this. I've been meaning to do breakout rooms more often, but with the amount of data material we go through. So there's 13. So let's do 3 of them. That sounds good. Okay.
Dr. Denard, can I ask if for or before the exam if Alex RTA is going to have another like review session where he goes over the old exams?
Yes.
Does he have a day for that already picked out?
Yes, it's on the, when is the exam's on the 18th, so it's on the 16th.
Okay.
Yeah, it's on the
Thank you.
16th. Yeah, you guys are lucky because last time when I taught this class, there was no such thing. So it was a bit of a scramble. So any volunteers here to tell me how you did this?
I'll volunteer.
All right.
So we inverted it,
Mm-hmm.
multiplied by CA, took the square root.
That's right. All right. So that's pretty straightforward. Like I said, this section of the class, not bad at all. You guys are gonna love it. The only thing you're not gonna love is if that part of feeding data is combined with mechanism. You see, so if you combine it, because it's really one thing, I separated them, but they're really one thing. If you combine it, then it could get a little complicated in terms of, if I say, okay, and I'm going to do an example of that in a minute, and then you'll see, you have an appreciation for how it could get a little complicated. But if it's just to fit data to curves and understand what the parameters are and determining them, it should be very straightforward to most of chemical engineers who took like numerical analysis and those types of things. So one thing I wanted to go over right now is if you have more than one reactant. And this is where some of the qualitative assessments can come in. You don't actually need, often you don't need to do, feeding the data completely to get, I'm gonna write this way. Okay, so you don't need to feed the data completely sometimes to get, to know what the order of the reaction is with respect to each reactant. Let's say you have a power law. Once again, let's say this is an example where it's with expression with more than one reactant. So in this case, we can take an A plus B type of reaction going to product. I should mention, right? If you have a reaction that is reversible, the same system applies. You just have to make sure you're operating at low conversion or far from equilibrium. One of those two, either with temperature or with concentration, so that you can look at the forward reaction independent of the reverse reaction. So you can now then later look at the reverse reaction. So if you think about how this works, it's very similar to chapter 1 or chapter 2 when we looked at thermodynamically consistent reaction rates. So if you determined the first one, if you're far from equilibrium, and then you are at very low conversion where the reverse reaction doesn't count or doesn't occur, then once you fit the first the forward reaction, you can guess what this reverse reaction can be. See, it all comes together. It's sometimes poetic how it comes all together. So, keep that in mind how this works. Okay, so you have to remember almost everything all the time. So let's say you have this reaction going to products. It's only one direction, and then you have minus RA is K, CA, alpha, CB, beta. Now, you need to set up experiments, like I mentioned earlier, where you set up experiments where, one experiment B is constant or in excess. So it's one of those two. And then A is varied. And then after that, you look at experiments where A is and actually that's all you need. That's all you need. you can look at experiments where A is constant if they exist and B is varied, but you don't actually need it. So now what does this look like? So if you were to take the first case where B is constant or in excess, you can write minus RA, which as KCB beta, and that's a constant, times CA alpha, and that's K prime CA alpha. So you can write it that way because, and we've done this before actually in some of our examples where let's say we have excess water for saponification, where the water is such high concentration, like 52 molar or something, where it doesn't matter how much of the reactant we react, it won't change. So yeah, so then if we take the log of both sides, so we have our log of K prime plus alpha log of CA. So we can calculate alpha and K prime. Okay, so we know that. And now if we, let's see, where am I? Yeah, then you can get K prime and alpha. Then after this, what you can do, you can rewrite you can go back to, I'm gonna call this I. So you can look at reaction expression I again, but you write it this way. Because you know alpha. So you can plot RA minus RA over CA alpha. And then again, you can take the log of both sides. So now you can calculate beta and K. See how this is how this works. Any questions about that? I have an example of it in Excel that I can show you. Then you can see how it actually works. So I'm gonna go ahead and share that with you. It's already worked out, unfortunately. So you just have to follow with me what has happened. Okay, so this is again a reaction where A plus B goes to C plus D, and minus RA is KCA alpha CB beta. So this is minus RA. Okay. Now this is the data you're given. So you're given an RA and it's calculated. So you see you're not given say either time or tau data here, because if you are given time, you'd have to go find a way to calculate the RA using the different methods we talked about before. But let's say you're given minus RA data and you're given A and B concentrations. These are concentrations. So what you can do is you can look at concentrations where B is constant. So we can pull those out and then A is changing. And this is the rate. So now what this means is that this minus RA is only a function of A. Its change is only a function of A. Oh, I think I know what I need to do. It's only a function of A. And you can take the log you can take the log of A and log of minus RA, same way. And I believe this is the plot for it. Yep, this is the plot for it. And it gives you an alpha of 1. So this is a first order reaction. And the K prime, which we don't actually need, I believe. So you can just get the alpha of 1. I don't think you need the K prime. Now, you can now go and look at the whole set of data, or you can look at the whole data now. Now you take log of RA over minus RA over CA. So you take the log of minus RA over CA for every point, and then the log of B. Okay, so now if you plot that, of course, these points in the middle, these points are all gonna be the same because it's the same concentration of B at 0.2. But you can plot this, and now you get a beta of 0.5 and a minus, and a log of K of minus 0.68. So then that gives you a K of 0.5, a beta of 0.5, and an alpha of 1. So effectively, this is 0.5 times Ca Cb to the 1/2. Okay. All right, so this is essentially how you would do that. It seems pretty straightforward. Now, the one thing to keep in mind is that now if this reaction is one of like the Langmuir-Hinshelwood types, where you have not only, you know, K, Pa, Pb, but is divided by 1 plus Kb, Pb, and Kc, Pc, and all of that. So you need experiments that cover all of these possibilities. So you can start not only be able to guess or hypothesize what the reaction rate expression should look like, could look like, I mean, but also be able to evaluate the different constants. See, here we're evaluating 3 constants, but in the case of the Langmuir-Hinshelwood, you could have up to 6 constants that you need to think about how to evaluate them by basically taking out of the data what the experiments, the runs that you want. So here we took the first 4 runs to be able to calculate because they're in constant B, and then you can have, and then you can then do the rest of the data. But if you have multiple variables that you need to calculate, so you have to go through and look at the data and then take from it the ones that would help you do your work. And then that's where we get to at the moment. So I will share my screen again with you, the other screen. Okay, is that the right one? Cannot tell. Yeah. Okay. So now let's look at something more complicated that you were unfortunately sort of tested on inadvertently. I didn't mean to test you on it, but that's why quiz 4 was such a ill-designed quiz. And I inadvertently tested you on that without realizing. It's not what I meant to do. So let's say you consider this toluene. I guess it's a hydrogenation of toluene, but it's catalytic hydrogenation, so it's kind of breaking it up. Consider this reaction, toluene with hydrogen, you know, on a catalyst, giving you methane plus benzene. So consider that reaction here. So let's say you have data. I'm not going to write all the data, but from a differential reactor. So this is a differential PFR where you get initial rates. Okay, so you have multiple runs. You've got your minus RTs, right? You have your RTs. Okay, then you have your toluene, hydrogen, methane, and benzene. You have all this data, and you've set up your experiment because you ran it. You want to determine now the first thing you want to do. You know this is a gas phase reaction with adsorption and surface reaction, so you know that it's gonna follow some Hinshelwood kinetics. So you know it's gonna follow that, but you don't know how. Okay. Now let's say that you look at your data and you say, okay, I want to find places where I can. You can ask certain questions. You can ask, is methane in the denominator of this reaction rate expression? You know, you can say, is benzene in the denominator? So you have products, so you can ask yourself, this reaction is not reversible, so the products are not gonna show up in the numerator. They're only gonna show up in the denominator. If they absorb on the surface, then they would, by absorbing on the surface, they slow down the reaction. You know, for example, you can ask yourself, is hydrogen absorbed? You can say, is toluene adsorbed? So you can ask those questions, and the data will tell you that. For example, here's what this could look like. Let's say you look at the partial pressure of methane, and then you have rate RT prime. So you take runs where everything else is constant, but the partial pressure of methane is changing. That's what you would do. If you do, let's say you do that and you find a flat line, nothing's happening as you increase partial pressure of methane. So that means that methane is not in the denominator. That means methane is not absorbed. So when methane is formed, methane leaves. So in fact, you can go from the data back to a rate expression, back to a mechanism. So you can work backwards, right? This is often what you would do. You would do the experiments and then you go back and forth. You go forward, test one. If it's not the right one, you go backwards. You work out a new rate expression with a new mechanism, and you go forward again to do the more tests. So let's say now you were to take benzene, which is another product, and you find that it goes down like this. So you know that benzene is likely in the denominator because as you increase pressure of benzene, the reaction rate goes down. So you know that is the case. So you can say B in denominator. And then methane is not. So let's look at the reactants now. Let's say you looked at pressure of toluene. With everything else constant, you find that the toluene pressure goes like this. This is an adsorption isotherm. So what that tells you is that toluene is in both numerator and denominator. So this is sort of hypothesizing what the reaction would look like. Now, I'm not showing all the data because that you're deriving this plot from the data. Now, in your case, you'd have to look at all the data and think about which one do I pick to plot each of my curves so I can do the assessment. And lastly, let's say we look at hydrogen, the pressure of hydrogen and the rate, and we see that it's straight. It goes straight up. What this means is that hydrogen is only in the numerator, because as you increase its pressure, it doesn't change. So that means your rate could look like this if it could look like this. It could also look like this. These are P's, by the way. You don't know which one it is actually. It's likely gonna be the first one. It could be the first one, but actually we can't tell. We won't say. So by doing the linear regression or the nonlinear regression, that's how you would find out which one of them is real. And I will try to, so I'll put homework 5B will have, I think, 3 or 4 problems. It's a pretty long homework. There will be 2 easy problems, and one of them will deal with that, this sort of stuff to fit your data using a more complicated Hinshaw-Wood stuff type of system, so that you can have some exercise expertise there. Okay, so in the last 10 minutes, we're gonna look quickly at the integral method. And then next class, we will start with nonlinear regression, which for some of you, once again, could be review, but it's essentially minimizing the sum of the errors. I mean, that's the sum of least squares. That's pretty much what it is. And then we'll look at residual plots, and that's in the book, chapter 6, I think section, you can basically read it ahead of section 6.4. Yeah, look at the statistical analysis of how you would differentiate between two regression methods that you use to evaluate your rate. So we'll go through that as the last part, and then we'll move into multiple reactions, and then we'll move on to energy balances, and it's gonna get super fun. We're gonna use Python next class. It's gonna be awesome. So you're gonna So that's what. So let's look at the integral method. So now this is all dealing with the differential method where we look at rate versus CA. So either we already have rate versus CA, or we convert time versus CA to rate versus CA using the methods I outlined here. So I outlined these methods here to differentiate between to convert. I'm also gonna post the Excel spreadsheet so you can play with it and see. It also has a nonlinear regression example that I'm gonna go over next class. So you could always look at that first before class as well. So anyway, let's finish with the integral method. So what the integral method is now, of course, it cannot be used for a CSTR, but it can be used when you derive your data using a PFR or PBR or an ideal or batch reactor. So you can derive that. So the only reason why you cannot often use it is because if you are to plug this in, and I meant to say this earlier, if you plug this in an ideal batch reactor rate equation, and you're like, okay, I'm gonna have to integrate this and then find a way to plot to determine the constants. You'll see what I mean in a moment. And then that's why differential method is probably the way to go for something like this. Now we can use nonlinear regression for both differential and integral methods, and that's going to be in the next class. We'll see how we do it. But you can imagine doing that pretty easily, where you would guess what KB, K, and KT are, and you would calculate a rate, or you calculate the concentration, and you would get the difference between concentrations, and you sum all the errors, and you ask solver in Excel to minimize all the errors while calculating the constants that give you the closest to the parameters, and that would be the way to do it. So, but we'll do that next class, and I'll show you. So when the data is in the form CA versus time or tau, you can use the integral method if you can if one, you can integrate the design equation as a function of CA and reaction orders. So let's say alpha. So if you can do that. And secondly, I guess that's all I wanted to say. If you can actually integrate it with respect to CA and alpha. So if you can do that. Or secondly, if you can linearize. So you can do linear regression. Or nonlinear regression. But for these, you have to plot something versus something, right? So you have to figure out how to plot it. So that's why you can use it. So what's the procedure? Very important first step in the procedure is that the rate expression is assumed. Okay, it's very important. You assume what it is, then you can solve design equation. In your third step, so you get a relationship between CA versus time or tau. right? And then you can linearize the relationship. And then fourth is to plot or do nonlinear regression. So this could be replaced with a nonlinear regression. Okay. So what does that mean? So imagine you have a reaction, you have a batch reactor. So much time do I have? 8 minutes, that's plenty of time, good. So let's say you have a batch reactor and it gives you CA versus time data. And you need to know, what if you can use the, you want to use the integral method to solve this. So you can say, okay, let's say that let's say I assume a power law. So it's a simple reaction, irreversible. Let's say you assume a power law of KCA to the alpha. Okay. Now you solve the design equation, and we've done this repeatedly. Now we'll keep it in terms of CA. So if you solve it, it's basically dCA dt equals RA, right? Equals minus KCA to the alpha. Okay. Now you can say, okay, let's say if you guess zero order, if you guess zero order, then your rate equation is dCA dt equals K or minus K. So if you get zero order, that's what it is. Then if you can, and then you know that at time equals 0, CA equals CA naught, right? So if you integrate this, you can solve CA is CA naught minus KT. So you can plot your data and solve for and solve for K, assuming it's zero order. If it's a straight line, it fits. If it's not, you have to guess again. So now let's say you guess first order. So now your dCA dt is minus KCA. You can clearly see how you can now use solver in Excel to do this, right? I mean, you can clearly see if you don't want to be guessing that way, you could basically solve it directly. And once again, if you solve this, you'll get the natural log of CA over CA naught equals KT. I flipped the signs. And if you have second order, and now it becomes 1 over CA minus 1 over CA naught equals KT. So you can plot these forms to calculate K, and if they're plotted in a straight line, then you can calculate K. Now, and you can do this at various temperatures, right? Then you can also calculate the activation energy. So if you perform at various temperatures, you can calculate the activation energy of the reaction too. So when you think of linearizing, so this is linearizing a power law. So let's say if you assume a Langmuir-Intro-Wood, this one is more difficult, but let's look at a simple one where you have minus RA equals this. Let's say this is what you have guessed, and then if you solve the design equation in the batch reactor, you will end up with this. So the question is, what do you plot against what? because you want to calculate what you want to calculate are Ka and K. So you need to figure out what to plot against what you can do is to divide by CA over CA naught. So if you divide, I think divide by CA naught over CA, just to take care of some signs. I don't want to keep carrying around. And if you do that, then you end up with natural log of CA over CA naught over CA naught minus CA equals KT over CA naught minus CA minus KA. So if you plot this guy versus this guy, if you plot these, then you can calculate K and Ka. So you can see how you can use the integral method, let's say from using data from a batch reactor. So yeah, we'll stop here. In next class, we will introduce nonlinear regression and how you can use it for, to calculate these rate parameters. And then we'll talk about, we'll do an example using Solver in Excel. Then we'll talk about the residuals and the estimation of errors. So that should take about an hour. It's not too much. And then at that point, you'll be able to finish all your homework. And this is what gets covered for the exam. And then we'll start talking about multiple reactions. And the book doesn't deal with Python whatsoever when it comes to that. It deals with goal-seek in Excel again. We'll do both a goal-seek examples, but we'll also use Python to solve multiple reactions. And then we'll introduce some notes about the choice of reactors for the reactions you want to run, depending on their effective orders and their the effective orders and their activation energies, whether or not they're endothermic, exothermic. So we'll do a lot of the qualitative theoretical sort of angles on that. So that would be a lot of fun. And then we can start talking about energy balances, which is going to take things to an awesome level. And I hope that you guys will enjoy energy balances as much as I do. They will be really, really fun. So if there are no questions, we will stop here and I will see you guys in 2 days.
Thank you.
Yeah, have a good one.